Check it out now, y'all.
NanoHub U, online instruction.
In this lecture, we're going to talk about relativistic kinematics. We're going to talk about how the equations of motion for objects are altered when those objects are moving close to the speed of light. And in particular, we're going to focus in on conservation of momentum, and we're going to look at how conservation of momentum is altered in relativistic collisions. So, as you all know, Newton's laws of motion are often used to solve kinematic problems at speeds that are very small compared to the speed of light. And this principle of conservation of momentum is an extremely useful principle that allows you to solve problems that involve the collision between two objects. So if you have two objects and you allow them to collide and then rebound, right? The momentum before the collision is always equal to the momentum after the collision, assuming there's no external forces that act during the collision. And so that's the premise that we're going to explore for relativistic collisions, and we're going to see if this momentum conservation breaks down when the speeds of objects become close to that of the speed of light. So that's the way we're going to proceed. I've put in an appendix in this lecture which reviews the non-relativistic aspects of two-body collisions. And I'll just say that, you know, you can write down an equation. If you have two objects, okay, if you have two objects labeled 1 and 2, the sum of their momentum before a collision has got to equal the sum of their momentum after a collision. That applies if there's no external forces that act during the collision itself. So this conservation law is discussed in a little bit more detail in the appendix, if you may have forgotten it or forgotten the principles that are behind it. We're going to analyze a sequence of 5 thought experiments to learn about conservation of momentum in relativistic collisions. So again, I choose to follow a path for this topic that tends to build some intuition so that you can see exactly where conservation of momentum fails when objects start to move close to the speed of light, right? So I try to build up some intuition by discussing these 5 thought experiments in some detail in order for you to understand how this principle of relativistic momentum evolves. If you're interested in important results for this lecture, I give you these important results in this table form right here. So you can refer to those when you're studying this material. Basically, a lot of the material I'm going to present is supplementary. It just allows you to understand what's going on. If you want the final results, this summarizes those results. So, what type of experiments am I going to analyze? Well, I'm going to think through a sequence of 5 experiments, and I want to analyze the momentum before and the momentum after a collision in interstellar space. So I'm going to take 2 objects. 2 objects are going to be 2 identical masses, and I'm just going to let them collide in different ways when these objects have relative velocities, one with respect to another. And at each experiment, there's 5 total. After each experiment, I'm going to analyze momentum before and momentum after, and try and reinforce to you when momentum is conserved and when it's not, and try to identify exactly where the problem is when we approach relativistic speeds. So the first one is a very simple experiment to follow. All the experiments I'm going to describe are based on this premise of 2 rocket ships. So I'm going to have a green rocket ship. I'm going to have a brown rocket ship, right? And these 2 rocket ships have practiced launching masses. Each mass is identical, and so we imagine these are the 2 masses that these rocket ships are going to launch. And in this first experiment, the rocket ships are at rest with respect to one another, so there's no velocity. And what the rocket ships do is simply just launch this mass downward. The brown ship launches this mass downward at a velocity u0. The green ship launches this mass upward at a speed u0. And the two objects collide, right? So they come together, they collide, and then they rebound and they go back to their rocket ships, okay? So the experiment is illustrated schematically in this diagram. And you can see this collision here just reverses the velocity in the up and down in the y direction, let's say, for the brown ball and the green ball. And so what you can do is you can write down the components of the brown ball and the green ball in the x direction and in the y direction before the collision and also after the collision. And what you find is that the collision just reverses the y component of the velocity. In this particular example, the x component of the velocity is 0. That's just because we've set it up this way, right? And what you can see is that if you sum up the momentums in the x direction after a collision, and you sum up the momentums in the x direction after a collision, you can see that they're equal to one another. And you can also see the same thing applies for the momentums in the y direction, right? Momentums in the y direction sum to 0. The momentum in the y direction after the collision sum to 0. This quantity is equal to this quantity, so momentum is conserved, right? So that's the first example. That's the simplest example that you can imagine. Perhaps the most, a slightly more complicated example now involves letting a rocket ship, the brown rocket ship, ship number 2, move at some velocity v sub f. Let's pretend that this velocity v sub f is much, much less than the speed of light. The same type of experiment is performed. At some prescribed point in time, this guy launches his ball at a velocity minus u naught with respect to his rocket ship. This guy, who's at rest, launches his ball upward at a particular point in time, and he launches it upward with precisely the same velocity u0. These two balls collide, they meet, so now the experiment is observed from the stationary reference frame, right? He would throw his ball straight up. The ball from the brown reference frame would be coming in. It would meet the ball that's thrown straight up, and it would collide, right? And that's the type of collision that we're considering here. So it shouldn't be surprising that if you calculate the momentum in the x direction, the momentum in the y direction, and you sum up those momentums, you'll find that the momentum in the x direction before collision is equal to the momentum in the x direction after the collision, right? The momentum in the x direction is now just basically given by the fact that this red rocket ship, or this brown rocket ship, is moving at a velocity v sub f with respect to this one. So that contributes the momentum in the x direction. Momentum in the y directions are exactly the same as they were in the first example. And so again, momentum is conserved very nicely here, right? Momentum before collision equals the momentum after the collision for both the x and the y directions. The third experiment gets a little bit more complicated because now we're going to give both rocket ships a velocity, right, opposite to one another. And we're going to ask the question, is momentum conserved for this collision as observed by you, a stationary observer that sees these two rocket ships moving past each other? So now what's going to happen is, right, the two rocket ships are going to release these balls. These balls are going to come together, they're going to collide, and then they're going to go back to their respective rocket ships, right? And we're going to ask, is momentum conserved in this type of collision? Again, this is an example of non-relativistic speeds. V sub f is much, much less than the speed of light. And if you track through the velocities in the x and the y directions before and after, what you find is, from a stationary observer's point of view, momentum is in fact conserved. So nothing surprising here. These first three examples are standard problems that you could have worked out when you took your introductory physics course, actually way back in high school, right? Because it's just a simple application of Newtonian mechanics. Now we're going to let the speed of these rocket ships increase so that they become comparable to the speed of light. And the question is, what changes when we do that? Well, the answer is, what changes is the velocity transforms have to be invoked. And so these are the velocity transforms that we calculated from the previous lecture, right? So as v sub f approaches the speed of light, we have to start to take these facts into account. And so the fourth experiment that I like to talk about is now ship number 2 approaches ship number 1. Both ships are moving at the same velocity v sub f, and v sub f is now comparable to the speed of light. What's different? Well, if you're a stationary observer viewing this lecture from your dorm room, right, you would see that ship number 2 is going to be length contracted. You would see that ship number 1 is going to be length contracted. These are due to the Lorentz-Einstein transformation equations, right? You would see the time runs slow on both ships because both ships are moving at velocities comparable to the speed of light. But nonetheless, this experiment where they both launch balls downward at a velocity u naught, right? That experiment is still conducted. And the problem is the velocity u naught that you would the velocity u naught that the ball is launched, right, would be measured by you in a stationary reference frame as a velocity u in the y direction. And you have to know what the velocity u sub y prime is in the reference frame of the reference ship. And then you also have to Lorentz correct for it using the appropriate transformation equation. Well, the guy in ship number 2 is trained to just launch the ball with a downward velocity, so there's no u sub x prime for that velocity of the ball. So u sub x prime is equal to 0, and so the velocity that you would measure would be u0 times this factor 1 minus beta squared, and it would be a velocity downward, so that's where this minus sign comes from. That's the velocity of the ball in from the red ship. The velocity of the ball that you would observe in the y ship, or from the green ship, would be a plus u naught times 1 minus beta, square root of 1 minus beta squared quantity, right? And in this example, what I do is I label intentionally, I label the balls M1 and M2 so that they're different, right? That helps us track through the algebra. So that's the experiment. Again, I have to go back and I have to ask, is momentum conserved, right? Is the momentum in the x direction the same before the collision as it is after the collision? And the answer is, for the momentum in the x direction, there's absolutely no problem. For the momentum in the y direction, there's actually a minus sign, right, that changes. But that's an interesting result. But if M1 is equal to M2, so if the two balls are identical, they have identical masses, this leading term cancels, right? And you would never know that there's a flip in the minus sign. So you would conclude that 0 is equal to 0. So momentum is conserved both in the x and the y direction, even though these balls are moving at relativistic speeds. Okay? Now, the fifth experiment is the one that causes problems. Because now what we're going to do is we're going to say, okay, let's pretend that this brown rocket ship is moving at a velocity v sub f. Let's pretend that the green rocket ship is fixed. And let's do the same type of experiment again, right? So the same type of experiment is, at some point in time, the guy on the brown rocket ship is going to launch his ball downward. It's going to have a velocity of u naught in the negative y direction. The observer on the fixed reference ship is going to see this velocity downward is minus u naught times the square root of 1 minus beta squared. So he would not measure that ball with a velocity of u0. He would measure it by with a velocity of that's corrected by the square root of 1 minus beta squared. The observer on the green rocket ship just throws his ball upward with the same velocity u naught. That's what he's been trained to do. The two balls will collide, right? When the balls collide, the green ball will bounce back into the rocket ship. The brown ball, the velocity in the y direction will be flipped in sign, right? And so after collision, the ball will move in this direction, and it'll move in this direction such that this rocket ship, in fact, will catch up with it and actually be able to collect it again. And so now the question is, from your reference frame, which is fixed with respect to ship number 1, right, is momentum conserved in this equation? And the answer is it is not, okay? And I worked through the table, right, in this case. Again, I label the masses M1 and M2 to keep them separate one from another. And what I find that momentum in the x direction is constant. So the momentum before the collision in x is equal to the momentum after the collision in x. You can see that the mass M1 before collision has 0 velocity because it's at rest. So the only momentum in the x direction is that attributed to the mass M2, which is the mass of the object in the brown reference ship. When I look at the momentum before and after the collision in the y direction, I get a problem, right? There's a flip in sign, and there's no way that this expression here equals that expression there. So this means that we would have to abandon conservation of momentum under certain circumstances when the velocities of reference frames are moving close to the speed of light. That's a very unsettling conclusion. And so we asked the simple question, is there some constraint, some additional equation that must be satisfied in order to recover conservation of energy, or conservation of momentum? And the logic is actually worked out in this box here, where it says, okay, if we insist that the momentum before collision is equal to the momentum after, what condition has to result? Well, we're just going to set this red term equal to the blue term, and we're going to insist that those two quantities be equal to one another. Well, what you find is, for these two equations to equal one another, what you find out is that the mass M2, which is the mass in the moving reference frame, so this is the mass of the object in the brown ship, has to equal gamma times the mass of the stationary ball, right? So the conclusion from this is you can recover conservation of momentum, but you have to require that mass M2 is actually greater than mass M1. And how much greater? Well, it's just this factor gamma that keeps popping up in special relativity. So this is the price you have to pay for conservation of momentum to occur when objects start to move close to the speed of light. So this result is completely general, right? I worked it out in the case of this simple example of two rocket ships launching identical balls with identical velocities, and I try to convince you that everything is fine when you're in a non-relativistic regime. You get the exact results that you would expect, but their problems start to develop when the speed gets comparable, when the speed of one reference frame gets comparable to the speed of light, right? Then conservation of momentum apparently breaks down. You can recover conservation of momentum by imposing this interesting condition. So turns out it's true. This is actually true, right? What you do is you define a relativistic momentum. Now, in terms of a mass M0, M0 is the mass of an object in a stationary reference frame, times its velocity v, but now you've got to multiply it by this factor of gamma. And this defines the relativistic momentum of an object as the object is moving close to the speed of light. You can make a plot of the relativistic momentum and you can compare it to the classical momentum. So classically, right, you can have any velocity for the object that you want. So v over c can exceed 1. There's no limit for velocities classically. Relativistically, we know that the fastest you can go is the speed of light. So as v approaches the speed of light, this ratio v over c approaches 1. And what you can see is this relativistic momentum shoots up to infinity the closer and closer you get to the speed of light. So this is the important consequence that comes out of this discussion, right? That in order to conserve momentum relativistically, you have to redefine momentum. The redefinition of momentum involves this additional factor of gamma. So that's the main point of this lecture. And the next lecture we're going to consider what happens to the energies of particles as they move faster and faster and they acquire speeds closer and closer to the speed of light. So we're going to consider masses that have extremely high velocities, and we're going to start to ask questions about their kinetic energies. And it turns out the kinetic energy also has to be modified by taking into account relativistic effects. So come on back for that lecture. We're going to talk about Einstein's famous E equals mc squared equation, and we'll provide a little bit more insight into how these relativistic momentums and relativistic energies are used in some straightforward calculations. So when you get a chance, take a look at the next lecture. It'll sort of wrap up our discussion of special relativity, and it'll summarize a lot of the important results associated with this motion of objects when they become comparable to the speed of light. So thank you for listening to this lecture, and we'll see you when you get a chance to listen to the next one.